So lots going on in the frozen yogurt world. I didn't realize it was that competitive or intense in terms of pricing. So we're going to start at Froyo Fusion. So the cost is 49 cents per ounce. Okay, so it says sketch the graph that shows the relationship between the ounces of Froyo Z and the cost of the yogurt F of Z. Okay, so if we graph that, what's it going to look like? It's going to be linear. All right, so it's going to be linear. We are going to increase, all right? Doesn't matter how much yogurt we get, there's going to be that same price, right? So it would start at 0, 0. It would go up by 49 cents each time. So it might look something like this forever and ever and ever, okay? So it is linear. If we wanted to put an equation to it, we could say F at Z would equal 0.49 times Z, okay? And then it asks you to find F at 16, all right? So F at 16 was just 0.49 times 16, which was $7.84. So what does that actually mean in this situation? Yeah, 16 ounces of yogurt of Froyo will cost $7.84. Okay? That's a pound of yogurt. Like, that's a lot. Okay, I'm hoping you're getting it in a container to take home and share with people. Okay, or you're going to be sick. All right, so that was at Froyo Fusion. So then we switch over. They decide to offer a special deal. So that if you get a cup that weighs exactly 16 ounces, then it's free. Okay, and we want to sketch that graph. Okay. So we're good until we get to 16 ounces, and then it's going to be free. So it would be 0. So I just put an open circle in there. But otherwise, it would just continue on its linear path. So it's going to have a hole in the graph. Okay, so let's talk limits. What's the limit as we approach Z from the left, approach 16 from the left? It's $7.84. So as I get close to 16 ounces, okay, whether it's less than 16, I'm going to pay $7.84. What about the other direction? Same thing, okay? And so then the limit for the whole thing would be $7.84, right? Okay. So what we could say is we would expect, all right, here's the context. We would expect any Froyo order close or very close to 16 ounces to cost close to $7.84. Okay? So that's what it means, all right? This is a piecewise function, all right? This is a piecewise function. We're $7.84 everywhere except at 16, because at 16, I get it for free, all right? So my cost at 16, or cost of 16 ounces is $0. So that's nice, okay? But if you go above it, and you got to hit it on the nose, right? You got to hit it at 16. If you've ever gotten frozen yogurt, do you ever hit it exactly on a specific weight very often? No. Okay? No. I've never been able to do that. I always go over. Have you ever had them like sliced deli meat for you and they're like, oh, and I'm like, I want a pound. Is, 1.01 okay? Yeah. Is 9995 okay? Yeah. So they'll ask you those questions, all right? So this is the same kind of situation. Think about the equation, all right? F of Z. Let's see if we can write that piecewise equation, okay? We're good at 49 cents. I don't know why I put a 0 there. 49Z. When is that true? Everywhere except 16. So as long as I'm not 16, it's 0.49Z. But it's 0 if Z is exactly 16. So that's my piecewise function. Would you say that function's continuous? No. Okay, we've got a hole in the graph. We have to pick up our pencil, graph the 0, and then go back to what we're doing. Okay, so then we go to the swirl and whirl. The names get better, okay, as we go. All right, so we go to the swirl and whirl. And at the swirl and whirl, the frozen yogurt shop across town, the cost per ounce is also 49 cents. However, if the cup weighs at least 16 ounces, the cost drops to 35 cents per ounce. Okay, so we want to sketch this graph. All right, so let's think about that one. Okay, so we're going to stick, all right, with 49 cents per ounce, all right, until I get to 16. But if I hit 16, what happens to my price? It goes down, right? It goes down to 35 cents an ounce. And so we're going to need to know at 35 cents an ounce, how much is that for 16? $5.60, something like that. Okay, so it jumps down. And then it continues to grow in that same manner. Okay, so we've got two linear pieces this time that break at 16 ounces. Okay, so I've got a piecewise function there again. All right, two pieces that break at 16 ounces. What would be my limit as we approach from the left side? What value are we getting close to? 7.84. Okay, it's 0.49 cents an ounce. All right, it's 49 cents an ounce. What about as we approach from the right? That's the $5.60. So the price changes, okay? And I got that by just taking 0.35 times 16, okay? What about the limit as we approach 16? Just looking at that graph. It doesn't exist, okay? It does not exist. Those two left and right limits are different, so it doesn't exist. And then F at 16, all right, is that $5.60. So let's write a piecewise function. Okay. So before I get to 16, I'm sticking with the 0.49. So that's true when Z is less than 16. Right? When I get to exactly 16, so greater than or equal to 16, it jumps up to that 0.35. Okay. Would we say this is continuous or discontinuous? Discontinuous. All right, discontinuous. It would for sure be discontinuous. Now, the question becomes, does Swirl and Whirl offer a better deal than Froyo Fusion? What do you think? This is an opinion question, so we could have lots of answers here.
Yes.
Okay. Yeah, if we go over 16 ounces, Swirl and Whirl is the better choice, right? What about if we're exactly 16 ounces? Yeah, Froyo Fusion's the best, okay? And then if we're less than 16 ounces, they're the same, okay? So it really depends. Depends on how much you purchase. Okay. What kind of discontinuity do you think we would call that one? Okay, what would you call this one up here? What happens to the graph? There's a hole. This is a hole discontinuity. Okay, there's a hole in the graph. There's a value for the function there, but there's definitely a hole in the graph. All right, what about this one? We call it a jump. All right, we go from one piece and then we jump to another spot and start again. So this is what we refer to as a jump discontinuity. But shift is a good word. All right, it shifts to a different place and we start all over. Okay, so that's referred to as a jump discontinuity. All right, and then finally we're going to the chill. All right, so we've been to 3 different yogurt shops now. And let's see what happens at the chill. Okay. At the chill, they take a very different approach. They will always charge $8 per cup regardless of how much it weighs. Okay. When, if ever, is this a good deal? Yeah, when we go over $8. So the more weight we order, the better the deal because it's only $8, right? But if I only order, let's say, a half an ounce, it's going to cost me $8 versus if I order 32 ounces, it's going to cost me $8. So it's a better deal if I'm ordering a large quantity. Okay, so it says to compare this pricing structure, to compare how this pricing structure compares to the other two, you decide to calculate the cost per ounce for various weights of froyo. Okay, what do you expect this relationship to look like? Any ideas? All right, so a decreasing function, right? I think that's a good idea, that it would be decreasing. All right, so the value would change. So if I have like 2 ounces, okay, it's $8. All right. What would the cost per ounce be? Cost per ounce would be 8 divided by 2, which would be $4. Okay. And so it asked me to do some calculations in that regard. So if a cup weighed 20 ounces, it's going to cost me $8. So my cost per ounce, 8 divided by 20 would be what, about 40 cents? Okay. What about for 16 ounces? Same thing, 8 divided by 16. It would cost me, what, 50 cents per ounce? For 4 ounces, 8 divided by 4, it would cost me $2 per ounce. Okay, so these are all per ounce. Okay, and if my cup only weighed a half an ounce, all right, $8 divided by 0.5 ounces, it would actually cost me $16 per ounce. Okay. That's a lot of money for some yogurt, right? We're taking that cost, we're dividing it by our weight. So what's happening to the cost per ounce as the froyo gets closer and closer to zero? As the weight gets closer to zero, what's happening to my cost? Yeah, it's getting quite higher, all right? It's increasing quickly. Okay, so if we wanted to sketch the graph, let's take some of these values that they gave me, all right? So we did 4 ounces, we said it was $2. At 16 ounces, we said it was 40 cents. At 20 ounces, we said it was 50 cents. And then we had 40 cents, okay? At half an ounce, we said it was 16, so it's way up here. So it looks like my graph is doing something like this. Is it ever going to cost me nothing? No, I'm always going to have to pay something, right? I'm always going to have to pay something. So this is definitely a decreasing graph, all right? If we look at what we did every time, okay, it looks like we have a horizontal and a vertical asymptote to this function, all right? Because, I'm never going to get 0 ounces, right? I'm always going to get something, but it's going to cost me infinitely more. I'm never going to get $0 because I'm always going to have a weight, right? So it looks like we have a vertical and a horizontal asymptote. Okay? The more I order, the closer it gets to 0. The less I order, the more expensive it gets. okay? So how does this differ from all the other from the other ones we looked at? Yeah, it's the only one that's a curve for one, all right? The other pieces have linear pieces, right? So this is a curve, right? And it is also considered, what would you think that the function would be? What are we doing to get the cost per ounce? It looks like exponential decay, right? It looks like exponential decay. But in reality, what we did every time is we took that $8 and we divided it by however many ounces we had. So it's actually rational. It's 8 divided by z. Okay? It's a rational function. And that's kind of weird to think about if I just look at the graph. So we had to look at what we were doing. Okay? All rational functions are going to have a discontinuity. All right? This is referred to as an infinite discontinuity. We're never going to approach or equal 0. Okay, it's an infinite discontinuity because we get that asymptotic behavior. All right. So what I want to do is to take all these different pictures that we've looked at and let's see if we can formalize a definition for what continuity really means. Okay, what continuity really means. So I'm going to go back and look at the first ones, all right? So let's look at the ones that we knew, this one that we knew was continuous, all right? It didn't ask you this, but what would be the limit as x approached 16 from the left for that function? $7.84, okay? What would it be if we took the limit as x approached 16 of f of z from the right? 784. And what was the value of the function at 16? 784, okay? Let's look at that next graph, all right? At this next graph up here, okay, we said the limit as x approached 16 from the left was 784, from the right was 784, but what was f at 16? It was 0, okay? When we look at this one, so we approached from the left, 784, approached from the right, 560. So the whole limit didn't exist and the value of the function was 560. What do you think is going to be key in us having something be continuous? The whole limit will exist. So the left and the right limits will exist. And what else was true in that first one? The value of the function will equal the limit, and that's the definition of continuity, okay? So the definition of continuity, if you want to prove that something is continuous, okay, first of all, f at that value is defined, okay? There is a function value, right? There's a value there. Second, the limit as x approaches c of f of x exists. That means both sides are equal. Okay? And then finally, not only does the limit exist, it equals the value of the function. Okay? So to prove that something is continuous, those are the conditions we have to meet. Okay, continuity, formal definition, is an existence theorem. This is what we have to prove is true in order to prove that something is continuous. All right, at an interior point of an interval. So I got this interval and I'm like, is it continuous at 5? Is it continuous at 7? All right, that's what we're going to check. We're going to check that f at 7 is defined, the limit as x approaches 7 exists, and it equals the value of the function. All three things have to equal. Now, if we're doing an endpoint, the only thing that changes, all right, the only thing that changes is we'll do a one-sided limit because I can't do both sides of an endpoint, okay? So we would check only one-sided limit. We check only that one-sided limit. So I want to start with something simple, okay, just for you to see, something that we know is continuous, and let's just walk through this process, okay? What does it look like when we're proving it? And then we're going to get to what they're going to kind of ask us to do, all right? And this is pretty much how we always see this continuity question asked, especially in multiple choice, okay? Now, discontinuities, all right? There were 3 that we talked about, all right? There was the whole. So I've got a function, all right? I may or may not define the function somewhere else, but I have a whole. Okay. The next type that we have is a jump, right? And in a jump discontinuity, all right, my graph's going to do something fun, and then it's going to jump somewhere else and do something fun. And the last one is an infinite discontinuity. It is an asymptote. Okay, vertical asymptote. The whole will also be titled sometimes a removable discontinuity, right? And we'll talk about that here in just a second. All right, so let's do a simple one, all right, for continuity. Is f of x equal to 2x plus 3 continuous at x equals -4? Now, that's a linear function. We know that all linear functions are continuous. There's no holes, there's no jumps, there's no asymptotes, okay? So let's talk about how we would prove it. First of all, we would find f at -4. All right, that's what we would do. So 2 times -4 plus 3 be -5. Okay. Then we would show our 2 limits, okay, because you got to show left and right. We would take the limit as x approaches 4 from the left of 2x plus 3, and the limit as x approaches 4 from the right of 2x plus 3. And I know this seems silly, all right, to show all of this, but it's what is expected, okay? How do we evaluate those limits algebraically? Substitute it in. All right, we're going to get, and those are -4s, by the way, 2 times -4 plus 3, -5. 2 times -4 plus 3 is -5. Okay, so therefore we can say it is continuous. All right, because the limit as x approaches -4 of f of x is equal to f of -4, which is -5. Okay, that's your proof statement. Right? AP is really finicky and picky about that. Okay, they want to know that you understand all the parts. Okay. Right? So that's the basic. That's one we know for sure. Okay? But now let's get into a function that maybe we don't know as much about. All right? It's piecewise. And notice this question changes a lot. Okay? So it says f of x is equal to x squared minus 9 over x squared minus 3x anywhere x is not equal to 3. And that it's equal to k, some value, when x is exactly 3. So let f be the function defined above. For what value of k is f continuous at x equals 3? All right. So in order for it to be continuous, the limit has to equal the value of the function. Okay? Well, I don't know the value of the function at 3 because it's k. Okay? But could I find the limit as x approached 3? Yeah. Okay? So we're going to start with the limit as x approaches 3 of x squared minus 9 over x squared minus 3x. Now, if we evaluate that limit as is, what's going to happen? It's all going to cancel out, right? 0 over 0. So we're going to have to use some manipulation here. Let's try to factor. Keep my limit. The limit as x approaches 3. The numerator would be what? X plus 3, x minus 3. The denominator would be x times x minus 3. And so we can indeed reduce. So it leaves me with the limit as x approaches 3 of x plus 3 over 3. Okay. We evaluate it. Okay, so 3 plus 3 over 3 gives me a value of what? 2. So k would have to equal 2. The value of the function would have to equal that limit. So my answer would be C. Okay. So they like this question in lots of different formats. Okay, so we're going to look at the next one, and it's just going to up the algebra a little bit, okay, and up our calculus knowledge just a smidge. Okay. So let's take a look at this one. Same type of question, all right, same type of question. It says g of x is equal to 3x minus 6 times the cotangent of x minus 2. When x is not equal to 2, and k when x is exactly 2. So we know f at 2 is equal to k. So what do I need to be able to figure out or to make it continuous? I've got to have the limit. I know the value of the function is k. I need the limit as x approaches 2. Okay, so let's do that. So the limit as x approaches 2 of 3x minus 6 times the cotangent of x minus 2. All right, and this is where all of our trig knowledge is going to come into play. Okay. All right. If I plug 2 in, 3 times 2 is 6 minus 6, that's 0. What is cotangent at 0? It's undefined, okay? So this is an indeterminate form, all right? So here's what we're going to do. We're going to have to get creative, all right? We're going to have to get creative, and let's use a trig identity. This 3x minus 6 and the fact that there's an x minus 2 right there just makes me think that maybe I need to factor that first parenthesis because there's an x minus 2, all right? How do we define cotangent? Cosine over sine. So this is going to be cosine of x minus 2 over sine of x minus 2. Okay, so all I did is just rewrite that trig identity. Okay. Now, one thing I noticed is that extra 3 is not really needed inside anywhere. Okay, so I'm going to pull it out in front. That's one of our things that we get to do with limits. I can pull that constant of 3 out in front. Okay. And I noticed that it leaves me with x minus 2 and cosine x minus 2 and then a sine of x minus 2. So I'm just going to rearrange that order just a little bit. Okay, so I just rearranged it a smidge. All right, did I do anything illegal right there? No, it's just commutative property, okay? I slid it over, definition of arithmetic. You should notice that we have one of those special trig limits right there, okay? And this is that reciprocal version of that sine of kx over kx. It's the reciprocal version. This whole piece right here is equal to 1, okay? That limit is equal to 1. So I have 3 times the limit as x approaches 2 of x minus 2 over sine x minus 2. That whole limit's going to be 1 times the limit as x approaches 2 of cosine of x minus 2, all right? This is my special trig limit that's equal to 1, okay, that we learned about yesterday. That's why knowing those limits is important, okay? So I'm going to keep the 3 was in front. That second limit's just a 1. And then for the last one, I can actually do direct substitution. All right, just plug in cosine at 2 minus 2, or the cosine of 0. What is the cosine at 0? It's 1. So I have 3 times 1 times 1, which is 3, and that is my solution. All right, that one's pretty intense. Did you agree? Yeah. Okay, that one's pretty intense. Okay, that one's pretty intense. All right, last thing I want to finish up with is continuity on an interval. We won't finish this whole thing. We'll do it tomorrow. All right, no big. Okay. But continuity on an interval, right? Continuity on an interval. Why that's important is because one of the things that we're going to have to establish for a lot of our theorems coming up is that a function is continuous over an interval. And so what that basically means is that is continuous over an interval if the function is continuous at every point in that interval. Okay, so if the function is continuous at every point in that interval, it's continuous on the whole thing. All right. Now, I put this little box here on purpose because these are things that are considered mathematical conclusions that we can use in proof. All right, somebody else long ago proved it, so we don't have to. We can use it. All right, the following types of functions are continuous at every point within their domain. Okay. Polynomial functions, rational functions, radical functions, trig functions, exponential and log functions, okay? If there's something that's not included in the domain, then it's not part of the where it can be continuous, all right? But it's continuous over its domain, all right? So we can use these. Okay? Because it would be really hard to prove continuity at every point of a quadratic. Right? Because how many points are actually on a quadratic? Infinite, right? There's infinite points there. And so it would take a really long time, all right, to prove that it was continuous everywhere. So we can use that, all right? We can use, hey, a quadratic is a polynomial function. Polynomial functions are continuous over their domain. Therefore, this quadratic is continuous over this interval, all right? So it's just a nice thing that we can use, okay? So take a look at this one. Right? The first thing it says is to determine if the function is continuous on the interval from 0 to 2. All right? This is a rational function, x squared minus 1 over x minus 1. All right? And so here's what we need to do. We got to figure out what's going on funky with this function. Funky functions. All right? So if I think about f of x equal to x squared minus 1 over x minus 1, if I have a rational function, I'm going to factor every last time. Okay? What would x squared minus 1 factor into? X plus 1, x minus 1. On the bottom, I would still have x minus 1. What happens in a function that shares a factor in the numerator and denominator? There is a hole, okay? There is a hole. Where does this hole happen to occur? At x equals 1, okay? There is a hole at x equals 1. So, does 1 fall on that interval from 0 to 2? Yes. Okay. So, is this continuous? We would say no, because there is a hole at x equals 1. Okay. So, we're looking for the exception to the rule. All All right, anything that would make it discontinuous. Okay. All right, let's look at the next one. Find any points of discontinuity and identify the type. What kind of discontinuity would we have? What should I do first? Factor. It's rational. Let's factor. So I have x plus 1 over, I don't know why I put a square there, x minus 3, x minus 1. Okay. Do I have any holes on this one? No. But what do I have on this one? I got vertical asymptotes. Okay. So I have vertical asymptotes. Those are discontinuities. Okay, the denominator cannot equal 0. Where are those asymptotes occurring? X equals 3 and x equals 1. Okay, so we have vertical asymptotes there. That is a discontinuity. Okay, because I can't equal, if I put 3 in, my paper explodes. If I put 1 in, my iPad explodes. Like, we just can't have that, right? And I don't know if Notability is ever coming back, and I'm so angry I can't even see straight about it. But that's another thought for another day. Okay, we have all this technology, and all of a sudden it's just crapped out. What the crap? Okay, last one. All right, last one. Describe the intervals on which this function is continuous. So this time, okay, it doesn't want me to tell where the discontinuities are. It wants me to tell where it is continuous. Play with that one a minute. All right, so talk to me about the issues. What are the problems in this one? There's a hole at 2. Anything else? Okay, we got vertical asymptotes at 4 and at 6. Okay, so if we want to describe the intervals on which it's continuous, we got to do everything but those values. Okay, so we're going to say we are continuous on. All right, we're going to start at negative infinity because we're good until we get to 2. And then we're good from 2 to 4. Then we're good from 4 to 6. And then we're good everywhere after 6. So it would actually take all of that, all right, to show all of your intervals of continuity. Okay, so basically we just leave out what's a mess. Make sense? Okay, so we're going to stop there. Number 12 will be your warm-up tomorrow. All right, so that's where we'll start as your warm-up. And I'm sorry that I copied that all on single pages. It used a lot of paper for no good reason. Unless you got one of the last 3, and it was front to back. So tomorrow we'll come in, we'll finish this. And so no wrap-up today. I'll just reload that for tomorrow, okay? And that's what we'll do. All right. So good news, if you've looked at the calendar, that's going to push your quiz back to Tuesday, which is probably good for everybody. Okay. All right. Cool beans. Good job. Good job.